it. And now we're on. Where we were last time was the integumentary system, thinking about the epidermis. The epidermis is that outer layer, and I just want to point out something about the epidermis. We made it very clear. The epidermis grows from the base, the layer we call the stratum basale. That's a very actively dividing layer, since we're migrating those cells up. By the new cells push the old ones up to the surface where they slough off. And some areas of thin skin, the trip from the basal layer, right there where the dermis meets the epidermis, all the way up to the surface only takes 15 days. Others, it's thicker skin and it takes about 30. That means we turn our skin over, meaning we replace all the cells in our epidermis every, 12 times to 24 times per year. An actively growing area. Now down below in the dermis and hypodermis, you do have cells that become damaged or become old and die, and cell division does replace them. But there's nothing like the rate of production that we see in the epidermis. We'd progressed through the structures of epidermis, dermis, and hypodermis. We were talking about skin color and the melanocytes, melanin being our principal skin coloring agent. But there are other indications of bodily health that are taken from skin color. One is called jaundice. The liver produces bile, and it's in the digestive tract, but after it does its job emulsifying fats, it is generally treated as a waste product, and it's broken down. Normally, it is disposed of through the urine and the feces, and it has a coloring effect on both of those under normal circumstances. If there's a buildup of these bile breakdown products, it's not being processed normally, there's the development of a normal color in the skin called jaundice. Now, of course, it is most apparent in those parts that lack color, so you'll often see a yellowing around the white of the eye. The pituitary gland stimulates melanocyte-stimulating hormone, and so if there is a tumor in the pituitary gland so that excess MSH is produced, then it produces a general darkening of the skin as the melanocytes crank up, start making more melanin. Addison's disease is also a disease of the pituitary gland with similar effects in skin darkening. Vitiligo is a curious skin coloring problem. It results from cells losing melanocytes and regions losing melanocytes. And if there are no melanocytes, then it's not possible to produce pigment. And so you end up with a white patch of skin. Now, often this takes on a kind of a patchy color rather than a gradation or a continuous color variation. The epidermis is also involved in the production of vitamin D3. You saw from our earlier study that calcium is our 5th most abundant element, mainly because we're vertebrates. Most of the calcium we have is locked up in our bone. The amount that's soluble is not only very low, but it's in a very, very strict control. So what do we need calcium ion for? Of course, we need it for bone growth and good, healthy, strong bones. But besides that, we need it when we want to contract the muscle, when we want to send a nerve signal or clot blood. So calcium is very important. It's a complex element in that you acquire it through your food. You have to have enough calcium in your diet. But even if it's in your food stream, it may not be absorbed. And this is what vitamin D is a part of. It has an effect on helping you absorb that calcium and getting it into your body. In this case, the epidermal cells, under the effect of UV light, sunlight on skin, produces this cholecalciferol, vitamin D3, which is converted into calcitriol, the form that aids your small intestines in absorbing not only calcium, but phosphorus as well. If you have insufficient vitamin D3, the bones can't mineralize. Now, as you go through more and more time and add calcium slowly, they will mineralize and strengthen. But here's what happens. Without sufficient mineralization, the bones actually remain weak while the body continues to gain weight, and the weight of the body causes the bones to bend out, especially the legs. This produces a condition called rickets. And rickets is more and more rare since we have addressed the calcium problem with food science. Our dairy products, especially milk, are all vitamin D fortified. And now that we're working more and more in front of computers and in offices, we get less sun. That's a lucky thing. But this is a person who suffered from rickets during their development. They have this bow-legged appearance. When they walk, rather than having a straight swing of legs forward, they sort of swing their hips. And you can kind of see the deformation of the skeleton. Notice this strange angle with the lower leg coming in at an angle to the heel. This makes it very difficult to walk. Now, I have been looking at, you think about rickets as an old-style disease, and mainly we have seen it disappear because of the way we have supplied calcium and vitamin D in diet. But I'm interested in do they treat it? I looked up several descriptions of rickets. All of the treatments involve re-breaking the bones and setting them and letting them heal in a straight line. So it's a very, very radical treatment to correct this. Epidermal growth factors made in the epidermis. It's very powerful, and it's a protein or peptide growth factor produced in salivary glands and in the duodenum, in the digestive tract. And it is most useful today in that it promotes growth in the epidermis. It is used artificially when we do skin grafts. There are times when skin is removed by injury or by burning, and the most efficient way of dealing with that is to graft a new piece of epidermis on top. What EGF does is it promotes the rate of cell division, so cells divide faster. It accelerates keratin production. It stimulates repair, which means fibroblasts and other fibers. It stimulates glandular secretion, basically speeds up all of the activities of the epidermis. And so below the epidermis, we find this dermis, which is not exposed to the outside, but which grades from a very adept connective tissue, a loose connective tissue called areolar tissue, something that the epidermis can adhere to by hemidesmosomes and form a very tight bond. And at the top, areolar tissue is more thin with a few fibers. It has those papilla that they're called, the dermis is called the papillary layer that anchors these epidermal accessory structures like hair follicles and sweat glands. You'll see it also surrounds the base of the nail. The outer or surface, closer to the surface, papillary layer is named for those mounds called papilla, and areolar tissue supports the dermal papilla. This is a more flexible and more stretchy layer. As you descend, you get to a border that has more and more reticular fibers, elastic and collagen fibers, and produces what's called a dense irregular connective tissue. Now, a rope is kind of only good in one dimension. You pull on a rope, it's strong when you pull on the direction of a rope. If you push on a rope, it's so flexible it just bends. But that means if you have stress pulling things apart up and down, and you run a fiber, a rope, like collagen, up and down, then it's reinforced against splitting. However, if that force is trying to pull the tissue right and left, you would have to put the fiber right and left. So the purpose of this reticular arrangement of these strong fibers is to have a fiber that's basically reinforcing in every direction. So this is good for tissues. that are going to experience stress or strain in unpredictable directions, not an everyday stress like the weight of the skin over the shoulder, but perhaps it's a fall where you're falling down and you scrape your elbow. Well, that's going to pull on the skin in a particular direction. It's the reticular fibers that are running along parallel to that direction of force that keeps the skin from splitting. That's why we get surface scrapes more than just splitting the skin open. Anytime the dermis gets irritated, especially the inflammation of the papillary layer, we call it dermatitis. Many causes. This is one of those things. Dermatitis is the inflammation. The cause of the dermatitis can be various. Infections can cause it. Radiation, sunburn is a type of mild dermatitis. Mechanical irritation like scrapes, especially those that penetrate the epidermis, and or chemicals. So the active ingredient in the resin of the poison ivy plant penetrates the epidermis and irritates the dermis, producing that rash and itching. It's an odd substance because it produces, in so many humans, it produces skin irritation, and yet deer eat it by the handful. So itch and pain is the signal that the derma is inflamed. The strength and elasticity comes mainly from two fibers, collagen and elastic. Collagen is our strongest fiber, and it bends easily like a rope, but it is so it provides flexibility, but it provides strong reinforcement when you pull it tight. It resists stretching. Whereas elastic is the opposite. It actually stretches to a longer length when you apply force, but when you let it go, it will spontaneously recoil and basically bring it back to that condensed length. So places where you're wishing to either resist flexibility or to limit the flexibility of the collagen fibers is where you find a lot of elastic tissue. A final factor for dermal strength is the osmotic pressure that's present in the cell. If we're properly hydrated, there's a certain firmness to the cell. But the cell can change in its skin turgor. It can go from limp and flaccid to very firm and strong based on the level of hydration in the cells. These contribute to these properties of the flexibility and resilience of the skin. Now, the fibers are not laid down in a consistent mat. We see that they're arranged in bundles that are laid down in parallel. So there will be a bundle of collagen fibers that is thick, and then an area that's thinner, and then another thick area. These alternating areas of thick and thin fibers are called cleavage lines, and they establish very important patterns. The fact that we're bipeds, we're up on our back feet, means that the gravity pushing down on our skin is naturally pulling harder on some parts of the body than they are on others. And this is reflected in the thickness of the skin. If you've ever been a leather worker and you've done various projects, if you're making a very fine, let's say, coin purse, you want a leather that's thin and flexible. But if you're making a harness for a horse to pull a buggy, you want very thick leather. And so if you look at the hide of a cow, the skin across the top of the spine, from the base of the head back to the tail, is the thickest leather, the thickest skin, and therefore the thickest leather. That's where you would get your strap leather for belts or strap leather for harnesses. The cleavage lines would be most close together there. So in a way, the pattern of these lines reflect the needs of the body of the animal you're looking at. Another important thing they have is that these cleavage lines actually establish an effect that affects healing. So if you make an incision in parallel between the cleavage lines, running in parallel, then though that cut bleeds less, it heals well, it closes well, and typically once it's clotted and healing has begun, it remains shut. Whereas if you cut across the cleavage lines, you basically are just looking at the ends of lines and trying to lace them together. That's very, very hard to do. And so a cut across is a cut that will be very difficult to close. It will pull open easily, so healing will be extended. And the amount of fiber that is needed to repair that cut and draw the wound lips together will be quite a bit of scar tissue, so the scar will be much more noticeable. These cleavage lines are shown here, front and back, and this irregular pattern is a typical pattern for bipeds that are standing up on their back legs, and the cleavage lines, for instance, on the shoulder are supporting the weight of the skin as it pulls down, hanging across the front and the back. You can notice a kind of a pattern that follows the support structures. If you start back here, you'll notice that this cleavage line descends the same way the rib does, comes around to the front and loops, and often here descends even further to provide support along the direction of stress. These very irregular patterns here circle the parts and basically reflect the way the skin is stretched and stressed when we move our limbs, either arms or legs. The pattern is much more complex on arms and legs, specifically because they're being moved so much. Flex and extend, abduct and adduct, rotate, circumduct, all of those movements that are made possible by the joints and the muscles that attach to them will stress the skin in a specific way, and these cleavage lines reinforce the stretching that causes on the skin. Now, the blood supply in the dermis is one that is considerably deeper than the epidermis, and so first, at the base of the dermis, there are larger arteries and veins along the reticular layer. This is called the cutaneous plexus, deeper, and it's running parallel to the surface of the skin. Now, running parallel to the surface of the skin, it means it's bringing the major blood supply down the skin, and basically providing supply for all the capillary beds above it. When those arteries branch into smaller arteries that then ascend through the dermis, up all the way to the base of the papillary plexus, they're going to be vertical, perpendicular to the skin surface, and they're going to basically allow the blood to rise through the dermis all the way to the base of the epidermis. This capillary network from the small arteries in the papillary layer is called the papillary plexus. The venous plexus is kind of in reverse, so from the capillary beds, venules return deep to the papillary plexus and the cutaneous plexus, and then eventually to the venules that are basically draining blood from the limb. If we damage these blood vessels, blood is released and produces a darkened residue that is cleared away during healing, but a bruise or contusion is generally a dermal feature. The nerves in the skin are of both types: sensory, sending messages toward the central nervous system, and motor, when those nerve impulses are coming from the central nervous system and asking for some kind of response. So the only thing they can control are muscles, glands, and fat. Those are the effectors of the motor nervous system. They do control nerve fibers in the skin control the sphincter muscles that can regulate blood flow. This branching tube system, if you put a ring of smooth muscle around an artery or an arteriole and you constrict it, it squeezes the arteriole and restricts or closes off blood flow. Other responses that occur in the skin are the signals that go to oil glands, that go to sweat glands, or specialized glands like the ceruminous glands that are present for earwax, or the mammary glands that are present for milk. Those are all glands that make and hold a specific secretion, but they have to be signaled when to release it. And that's a nerve issue. Sensory receptors are found in the dermis, and they provide information about the outside world. Tactile corpuscles are in the dermal papilla and basically can pick up very, very light touch. Deep pressure and vibration will be a nerve that has a larger corpuscle, many, many layers, and also is buried deeper in the dermis, because although these are both contact signals, they're very different. The one might tell you that a tick is walking on your skin surface, or it might tell you that a breeze has disturbed the hair on your arm. Those are very light touch and sensory messages. Whereas if you are, let's say, carrying a box, you set that box down on your hand on top of the desk, if it's heavy enough, it's going to crush your tissues. Then a deep pressure or a vibration nerve ending would send a signal, get your hand out of there. Those are both touch, but they're different kinds of messages. So here we have the dermis shown in pink. Notice the lack of fibers drawn up here. This is the papillary layer. Here is the papilla. And as you go down, here are the more and more and more dense fibers, collagen and elastic, that form reticular networks of this dense, irregular. So what that means is that you stress the skin, pull it in this direction to the left, and the epidermis slides with it. And this papillary layer flexes more because of the absence of dense fibers. But just as it gets a certain distance, these fibers come tight and resist further movement, allowing you to preserve the skin without splitting. Here is the cutaneous plexus at the base of the reticular layer, and these are the rising arterioles supplying capillary beds all the way up to the papilla of the dermis. Anything that occurs up here in the papilla is going to be very sensitive. So this naked nerve ending, the most sensitive. These small corpuscle endings, those are relatively still very sensitive if they're shallow. But as we bury them deeper, here's a lamellated corpuscle. See all those layers? And this central sensitive nerve ending is buried below them. That means you have to have a lot of pressure to compress the tissue and compress the surrounding layers and produce a nerve impulse that signals a danger point for deep pressure. Accessory structures of the dermis are anchored in the dermis, even though it is epithelial, epidermal tissue that gives rise to them. The thing to notice in these drawings is even though this hair follicle is anchored way down deep here, probably all the way down to the reticular layer, notice these moist layers of the epidermis, the stratum basale, spinosum, and granulosum. When they get to this cylinder, the hair follicle, those cells turn the corner and form a significant layer, in fact, the propagating layer, all the way down to the base of the hair follicle. As it ascends up here, you'll notice that it is that epidermal tissue that also gives rise to this sebaceous or oil gland. So the way this works is the same way the skin works. What did we notice with the epidermis? Grow from the bottom as the cells are produced. Expand them, keratinize them, color them, and then move them by producing more cells below. And that's what's happening. The region of cell division and polymerization is right here at the bottom. So the blood vessels bringing materials in are supporting very rapid cell division. those new cells expand. Now they can't go down. This sheath holds them against that direction of movement. So the new cells, as they're expanding, push the old cells ahead of them. Now the cells are going to be more heavily keratinized than in the skin. So skin is flexible and it's soft. Hair is somewhat more stiff and it forms a definite central cylinder. It can be very fine and limp, or it can be relatively stiff and bristly. The hairs of different animals are used for a variety of things. So bristles from pigs were especially the larger and related to wild pigs, those bristles are often used for hair brushes. So hair grows from the base outward, and an actual longitudinal section shows you some of these features. You don't see the blood vessel down here, but you see this little kind of fork-like opening. This is where blood vessels and capillary beds are providing oxygen and nutrients to the dividing cells in this very base of the papilla of the hair bulb. These living cells are moving up, being keratinized, being pigmented by melanocytes, and as they move away, as the keratin becomes denser and denser, it forms an actual shaft of hair, and as it goes further and further, it dries out more and more, so halfway up, it's going to start to scrape against this. This is where the sebaceous gland introduces oil to lubricate the hair and allow it to slide through that shaft and out of the opening at the surface of the skin. So one of the reasons that hair is you can manipulate it in so many ways is that it is a dead structure. Keratin is something that retains its stiffness and its body, and so you can curl it, you can straighten it, you can color it, you can wash it. Basically, it's very resistant to that type of treatment. Now, the glands that occur in the skin, I've already named them sebaceous for oil glands, and the oil is called sebum. This is a holocrine secretion, meaning that it's a stratified layer, and the cells grow and fill themselves with oil, and then the entire cell breaks down to release that and all the cellular contents. There are two types of sweat glands, apocrine and merocrine or eccrine glands, that produce watery secretions. We do lose water based on insensible perspiration. That's mainly through the skin. The sweat glands are releasing water mainly for thermal regulation. This is the sweat we notice. And whether we're heating a part of the body and sweating locally, or doing something like exercising and heating the entire body up, we will have additions of that surface wetness based on the two gland types. Mammary glands came from sweat glands, but in this group we call mammals, it's been highly modified to produce high volumes of nutritious material, mammary secretions. Ceruminous glands, because the earwax is called cerumen, and it really comes out as an oil, not a wax. High up in the ear canal. Now here's a problem. The tympanic membrane is very delicate. It's responding to wavelengths of sound moving through the air. So in order to vibrate when those hit the tympanic membrane, it has to be very delicate. However, being very delicate means it's subject to damage. So it's placed high up in a canal here in the side of the skull. We'll talk about the auditory meatus when we get to the skeletal system. So it has to be very protected. Up there close to the top of the auditory canal, there are ceruminous glands that are letting this oil out, and it coats the inner wall of the passageway and flows down. As it flows out, it's a wall where particles contaminants hit the wall and stick. And this constant outward flow is supposed to carry them out. So I'm sure some of you have noticed white flakes of a kind of a waxy material coming out of your ear. That's the hardened or congealed earwax. So this is a natural process to protect the eardrum and to keep the auditory canal open and clean. Today, with the invention of Q-tips, we've become kind of overactive on scrubbing those out. And so earwax has a somewhat reduced effect in our modern culture. Sebaceous glands and sweat glands are controlled in various ways. The autonomic nervous system, which is a subconscious part of the nervous system, will control both oil release and the apocrine sweat glands. Apocrine sweat glands are for thermoregulation and will release sweat all over the body. Oil, likewise, is released all over the body. American sweat glands are somewhat different. They work locally and are controlled independently. That means, let's say you're driving in the winter. You're driving west and it's noon. It's December, and a bright sun is shining on your left side. So it's very cold outside, and it's cool in the car. But your entire body, except for your left arm and shoulder, is in the shade. It would be American sweat glands that would respond and attempt to cool this part of your body, but would not need to invoke sweating over the entire body. Thermal regulation works because blood picks up the heat where it is, wherever it is, and mixes it with the blood and distributes it all over the body. And it's the main function of sensible perspiration and the evaporation of it to pull that heat out of the body. So the cardiovascular system, again, links this function to the function of the skin. The skin is the radiator, and the blood is sort of like the antifreeze, carrying the heat to where it can be shed. Second accessory structure is a nail. Now, what did we see with the skin and the hair? Grows from the base, surrounded by epidermal tissue. Basically goes through a process of cell division, cell expansion, keratinization. A lack of pigmentation is characteristic in the nails. These are the most keratinized cell in our body. They produce a hard sheet with a sharp edge. Nails in some individuals can be grown, and they're basically malformed, bent, so that they produce a small blade. And in the Aborigine people of Australia, it's been observed that often people will grow the nail of their thumb and basically flex it and cause it to grow with angles and kind of a stiffness, and it will be sharpened to the point where it can be used in some knife-like actions. Nails are made by dead cells packed with keratin. Nail structure, because it's an actively growing area, just like the hair, they grow out and need to be trimmed. They're growing from a deep location. You'll notice clear down here at the base near the phalanx bone, we see the root of the nail where cell division is beginning, and pushing against this firm backstop, pushing these cells outward to eventually emerge from beneath this eponychium and reveal the surface of the nail there on the upper surface of each digit. You can see the area of cell production, and as they move here very quickly, the cells are keratinized, in this case not so much pigmented, but they die, so that the nail is actually a living structure. The nail protects, so it is very difficult to get something under your nail in the nail bed, but once it's there, it's very difficult to treat. Nothing penetrates through the nail, and so if nail fungus gets established, they often remove the nail, or now they do have some fungicides that they can administer orally, but it takes 60 to 90 days for the circulating blood to carry enough fungicide to clear those growing fungal cells from this nail bed. But it is possible. Now, another great feature of the integument that you would absolutely suspect to be important would be the repair of injury. And we're going to look here at a cut. This cut is bleeding. Notice how the cut has parted the epidermis up here, has produced a wall, an edge along the dermis, and it has penetrated all the way down to the border of the hypodermis. Along the way, it has severed some of these blood vessels, mostly arteries are shown, which are continuing to drip blood. Now, they trigger an inflammatory response. The cells in this region are exposed to air, to different temperatures and dryness. And as a result, stimulates a change in mast cells and other cells that basically will help identify this region as an injured region. Now, the mast cells release things like histamine, heparin, prostaglandins. You can think of those as damaged chemicals, and they basically are going to start recruiting all of the repair and healing crews from around the body, the different types of cells that are needed to repair this break in the skin. So the first thing that does happen as a result of the bleeding is that trench fills up with blood and congeals through clotting. Fibrin is the fiber that's produced and basically blocks the movement of red blood cells and produces this scab. After several hours, when the scab has kind of stabilized the region, we notice a curious thing about the epidermis. The epidermis and the stratum basale are the most actively dividing cells in the region, and they actually begin to migrate down the edges of the wound. So you can see them moving down on both sides, which tells you, just like the base of the epidermis, just like the base of the hair and the nails, if you're going to produce something new cells, the epidermis is going to be involved. Other features of this figure, you see that macrophages have arrived. Macrophages can fight debris. Maybe you got some sand in the cut. Maybe you have bacteria there. They can also attack pathogens and potentially infectious agents. And we start to see the appearance at the base of this clot something new, kind of granules and eventually fibers. What we're going to do is we're going to produce fibers that span this opening and basically attach out here into the good tissue, and then basically provide a net across the bottom that cells can migrate into, take residence in, and begin dividing. Fibroblasts are going to perform this function. Fibroblasts are those cells that will manufacture this fiber connection. And you'll notice as that previous region of injury is filled in with fibers, the epidermal layer, which now, the epidermal layer, the stratum basale, migrates upwards with it. Doesn't remain down here. What is being formed down here by cells migrating out onto this fiber network and proliferating, restoring the kinds of cells that are in the dermis, providing a kind of a support structure for them to operate and to complete the healing. You can see it's kind of halfway healed here, and really the way this is working, tying good tissue on this side and good tissue on this side together, sort of like the laces on a boot. So you basically put in a new good lace and tie it into these fibers over here, and then that provides a connection which will resist stretching and reopening of the wound. Eventually that migration upwards is completed. Here's now an intact epidermal layer on top of this repaired layer of scar tissue. The scar tissue does go deep on the surface. Often there is some kind of depression, showing you the character of these new surface regions that have been knit together, and that area is stabilized. The epidermis has an effect on many different treatments, and one of the things that's really difficult to treat is the removal or the injury of skin by burning. It turns out that you can cut, mangle, scrape the epidermis, but if you remove it completely, it does not regenerate very quickly. And while the dermis is exposed, it's very dangerous with respect to dehydration and also very painful. So these kinds of figures are developed. So you can estimate the total surface area affected by burns when you're classifying a burn. First degree burn might be a bad sunburn. Second degree burn usually involves some kind of blistering and breaking of the epidermis, but it typically is not damaging the skin so deeply that you can't recover from it. Burns that remove the epidermis and damage the dermis are those that need to be treated by covering the area, hydrating the area, and typically doing a skin graft that introduces an active epidermis back into the area and using epidermal growth factor to promote its attachment. Now, this is our first organ system, and I'm going to talk about the era that you have chosen to study medicine. And this is the era when the baby boomers, starting in around 1945, the baby boom began. There was a huge population that followed, a huge number of births that followed the ending of World War II. So you will be encountering many, many opportunities in medicine to treat the aging or elderly. We're going to use that as a reason for talking about the effects of aging system by system all the way through the reproductive system at the end of ANP2. So the general features will relate to cells. Cells become less vigorous. They divide slower. In some cases, they do not replace them, the cells that turn over, that die. And so tissues actually shrink as you reach that switch point from robust older life to geriatric decline. So what do we see in the skin? The epidermis thins. It actually loses thickness, and that has a big effect on both the sturdiness of the skin. It feels thinner, flimsier, but it also does not retain heat as well. If you've ever had an elderly friend, you go over in August and it's 95 degrees outside, you get out of your car and you walk up, and there they are on the porch with a sweater on. And the reason is maybe 95 outside, but they're cold. Likewise, they're less resistant to heat on their skin. The number of dendritic cells, branched cells, goes down, so the sensitivity of the skin is decreased. Vitamin D3 production goes down, and therefore calcium balance can become an issue. The melanocytes begin to operate slower and slower, and pigmentation is lost. Most noticeably is probably in the hair, as people, their hair turns from its lifelong color into gray or silver. All glands decrease in their secretions, and in the skin that means sweat and oil decreases. So the skin becomes dry on the surface and papery. It often needs more of a lotion or a softening treatment to keep it pliable. The blood supply of the entire body is reduced as you go into aging. On the skin, that means that there's a restriction of blood flow through the surface of the skin. Hair follicles decline in their activity, and so hair becomes thinner. Its color change we've already talked about, and even the loss of hair is prominent. Elastic fibers all over the body lose their elasticity, and the proportion of elastic fibers goes down. So flexibility, pliability that you've had since birth is diminished. Hormone levels generally decrease, so chemical regulation diminishes, and the overall repair rate, so of skin contusions, the time to healing and the satisfaction you get from healing, the restoration of a painless and healed sore, in fact, declines as those spots and wounds in progress persist over a longer period of time. So we see this in aging. We're going to notice, for example, that bones lose mineralization, that muscles atrophy. We're going to notice the brain actually shrinks, which is one of those things that affects memory loss and mental performance. So this is our first trip through the aging integumentary system. So, end of the recording, which we will call 5B.